A single 24-hour rotation of the planet is normally a predictable metric of calendar time, yet a profound spatial paradox can completely shatter these baseline expectations. In south-central China, the traditional boundaries of seasonal precipitation were obliterated when a single day produced close to a full vertical meter of water descending directly from the sky. Specifically, 713 millimeters of rain fell onto a single county in one 24-hour cycle. To evaluate this through the lens of geophysical systems analysis, this volume represents more precipitation in one day than many global metropolitan centers receive in an entire annualized cycle. The familiar rules of meteorological progression, where a storm system traverses a landscape and distributes its moisture along a linear track, were replaced by a localized vertical stacking of hydraulic mass. The water did not spread. It accumulated over a fixed geographic point, transforming a standard weather anomaly into a severe structural crisis. The true scale of this crisis is anchored in precise metrics and documented administrative escalations. On July 3rd, a tropical cyclone, identified in early reports as Typhoon Maysak, made landfall on the southern coast of China, pushing inland over the Guangxi Zhuang Autonomous Region. As the system advanced into Binyang County, under the direct administration of the regional capital of Nanning, the sheer density of the downpour rapidly exhausted the natural absorptive capacity of the ecosystem. Within hours, local soils reached absolute saturation, converting the terrain into a zero-capacity runoff plain, where every additional drop of rain sheeted off hillsides directly into the regional watershed. This unprecedented volume immediately challenged the safety margins of civil infrastructure. Engineers designed dams, embankments, and spillways based on a calculated return period, the statistically modeled once-in-50-year or once-in-100-year design storm. A 28-inch single-day rainfall total sits so far out on the tail of this probability distribution that it entirely bypassed the structural safety margins of the older, aging infrastructure engineered to manage this network. Operating far beyond its design limits, the entire regional water control grid began operating on borrowed time, precipitating a cascading destruction of protective barriers. In response to this systemic deficit, authorities in Nanning were forced to elevate the flood control emergency to level 1, the absolute highest tier in the nation's four-step emergency response framework, reserved exclusively for uncontained regional catastrophes. The physical toll of this infrastructure deficit manifested rapidly across the watershed. At approximately 11 o'clock on Monday morning, local time, the Luonan Reservoir suffered a catastrophic structural failure. This facility was documented as the largest medium-sized reservoir in the area, holding back an immense static load of roughly 93 million cubic meters of water. This volume is equivalent to tens of thousands of Olympic-sized swimming pools, stacked behind an earth and concrete barrier that had already endured days of unremitting pressure. The dam did not merely overflow. The internal structural integrity failed, cracking open at two separate points. These twin breaches rapidly widened and merged into a single expanding fissure, measuring approximately 50 meters across. The mechanical logic of a dam breach dictates that the width of the gap, combined with the depth of the reservoir, governs the acceleration of the discharge. What escaped was not a clean surge of water, but an explosive, churning wall of mud, uprooted trees, and structural debris that tore through downstream populated areas. In neighboring sectors, the crisis instantly multiplied into a systemic cascade. The Yunbio Reservoir was overtopped and breached. The Sancha and Chaiwan reservoirs sustained severe structural damage after overtopping, and the Laiwang Reservoir began spilling over its embankments. 5 water control structures failed or teetered on collapse simultaneously, fracturing the emergency response capacity as crews were pulled in every direction at once, leaving over 300,000 people affected, 50,000 evacuated, and thousands trapped on rooftops facing critical shortages of clean drinking water. The profound, counterintuitive core of this disaster lies within the comparative physics of the Western Pacific atmospheric basin. At the exact moment Maysak was dismantling the infrastructure of Guangxi, a secondary, vastly superior thermodynamic engine was active in the region. Super Typhoon Bavi, a massive system that had already devastated islands in the Marianas. By wind speed and kinetic energy, Maysak was the smaller, weaker system. Yet, in the strict physics of precipitation-induced disasters, kinetic violence is a secondary variable. variable. The primary determinant of mortality and structural destruction is duration. A moving storm, distributing its rainfall at 25 kilometers per hour, limits its localized volume, whereas a stalled system delivers a continuous, high-volume rain rate to a singular coordinate for days. Maysak did not stall because it possessed internal strength, but because the macro-scale atmospheric steering currents, the high-pressure ridges, and monsoon circulations that act as a conveyor belt, suddenly equalized and ceased to push. The sky stopped moving, and the storm became a stationary hydraulic machine, continuously drawing warm, saturated air from the South China Sea and wringing it out over the exact same valleys. This systemic breakdown leaves researchers with a critical diagnostic puzzle. As global background temperatures rise, expanding atmospheric moisture capacity by roughly 7% per degree Celsius of warming, storms are handed increasingly volatile energy reserves. If the structural limits of our historical civil infrastructure were designed around moving systems, what happens when the steering currents of the planet fail entirely, transforming a theoretically minor, low-wind anomaly into an immovable, infinite engine of regional erasure? To fully comprehend the magnitude of this cascading network failure, we must look to the historical reference class, established over half a century ago. In August of 1975, a decaying tropical system designated as Typhoon Nina stalled over Henan province. It exhibited the identical thermodynamic signature observed today in Guangxi, dropping over a meter of rain in 24 hours onto a saturated landscape. The result was the Banqiao Dam disaster. When Banqiao collapsed at the head of the watershed, it triggered a rapid-fire chain reaction downstream, causing the near-simultaneous structural failure of 62 separate dams. The immediate hydrodynamic surge claimed an estimated 26,000 lives, while the subsequent systemic collapse, famine, and waterborne disease vectors pushed the total long-term toll well into six figures. Banqiao stands as a stark physical proof of what happens when a water control network is pushed past its ultimate structural limits. This historical template explains why seasoned geophysicists refuse to view the current crisis in Guangxi as a series of isolated events. A single dam failure is a localized emergency where resources can be concentrated. A 5-reservoir cascade is a fundamental system failure because every upstream breach injects massive, uncalculated kinetic energy and fluid volume into the reservoirs below, overloading each subsequent structure in a deterministic chain dot. When a disaster of this scale shatters a region so suddenly, a predictable socio-cognitive phenomenon occurs online. Speculative claims spread rapidly, suggesting the event was deliberately engineered via high-frequency atmospheric heaters like HARP, cloud seeding operations, or covert physical sabotage. Evaluating these claims through the rigid laws of thermodynamics reveals their baseline scientific impossibility. The kinetic and thermal energy circulating through a mature tropical cyclone operates on an order of magnitude between 10 to the 14th and 10 to the 15th watts. This energy budget represents a massive fraction of the entire energy output of human civilization, running continuously. No artificial installation or anthropogenic technology commands even a fraction of the energy required to manufacture a typhoon, steer its trajectory, or force a massive system to park itself over a specific province. Cloud seeding can merely alter the microphysics of an existing cloud structure to encourage localized condensing. It cannot generate an infinite rain machine. Furthermore, forensic evaluation of the breaches themselves shows the textbook signature of overtopping and hydraulic erosion, where water breaches the crest and cuts through earth embankments until the structure liquefies under pressure. This is the unmistakable physical fingerprint of infrastructure being utterly overwhelmed by sheer volume, not targeted demolition. The true diagnostic inquiry must focus on the structural vulnerability of the infrastructure itself, examining why these aging barriers were operating on such razor-thin margins. Extreme rainfall does not stress a civil engineering network uniformly. It seeks out the microscopic structural flaws, the unmaintained embankments, and the compromised spillways, applying relentless physical load until the weakest link yields. This structural stress shifts directly onto the human component of the system. The simultaneous failure of multiple reservoirs fractures the logistical capacity of emergency teams. When 5 separate nodes threaten collapse at once, rescue crews are divided across divergent coordinates, forcing forced to make impossible choices regarding which valley to evacuate and which breach to reinforce, while the very access roads required to transport heavy machinery are swallowed by the rising waters. This spatial isolation suppresses the rescue rate exactly when velocity is most critical. Currently, the recorded human toll stands at 30,000 displaced, over 50,000 evacuated, and at least 300,000 individuals severely affected. However, systems analysis of fast-moving flood events dictates that these early casualty metrics represent an artificial floor. When villages are entirely cut off from communications and transportation networks, early reporting is always suppressed. As physical access is progressively re-established across the flooded zones, these statistical curves inevitably trend upward. The immediate outlook suggests we are not viewing the aftermath of a completed event, but rather the midpoint of an unfolding systemic crisis. The leftover cyclonic circulation of the storm continues to dump heavy precipitation directly over the compromised reservoirs of Guangxi, compounding the stress on barriers that are already fractured or actively overtopping. This ongoing loading of a damaged system introduces extreme instability. Simultaneously, the physical threat is migrating. Meteorological models indicate the remnant low-pressure system is drifting northward, projecting this exact same high-duration rainfall mechanism toward the highly populated provinces of Hunan, Hubei, and potentially Jiangsu. These territories contain immense population densities and extensive agricultural assets, all relying on water management systems that face the exact same atmospheric trap. The macro-scale weather pattern remains frozen, meaning the background conditions that permit a weaker storm to outkill a fast-moving monster are still active. With the immense engine of Super Typhoon Bavi still operating concurrently in the Western Pacific Basin, the regional stability of East Asia's water control architecture faces an unprecedented, multi-layered structural test, where the ultimate limits of human engineering are being forced to confront the raw physics of an unmoving sky. The progression of this hydrological crisis now depends on a clear sequence of physical variables, each operating as a critical failure point within an interconnected regional system. The immediate stabilization of the damaged infrastructure in Guangxi represents the first defensive tier. Emergency crews are operating against a harsh mathematical reality. Every single barrier they manage to secure or reinforce prevents a catastrophic, sudden release of kinetic energy downstream, saving whole valleys from experiencing the explosive mud and debris surges that characterize the Luonan failure. If a compromised dam holds, the downstream surge remains zero. If it gives way, the loading on the next downstream node multiplies instantly. This binary outcome is being decided hour by hour along the banks of the regional watershed, where the physical integrity of packed earth and concrete faces an unyielding static load. The margin between a managed containment and a widening regional disaster is measured in the meters of remaining spillway capacity and the structural resistance of saturated embankments that have been under continuous pressure for days. Simultaneously, the secondary phase of this crisis is unfolding at a broader geographic scale as the remnant atmospheric circulation shifts its coordinate focus. As the low-pressure system drifts northward out of the Guangxi Zhuang Autonomous Region, it carries its vast reservoir of precipitable water directly into the river networks of Hunan, Hubei, and potentially Jiangsu. These provinces represent a massive escalation in systemic exposure. The population density of these central and eastern territories is exponentially higher, meaning that the identical stalling mechanism, where an unmoving atmospheric pattern stacks a meter of water over a single coordinate, will interface with an urban and agricultural network of vastly greater complexity. The rivers in these northern paths are already receiving the preliminary runoff, and their banks are steadily climbing toward their maximum flood season thresholds. If the atmospheric steering currents remain paralyzed, the exact same mechanical sequence observed in Binyang County will replicate itself. Instantaneous soil saturation, total conversion of rainfall to immediate surface runoff, and the rapid overloading of infrastructure designed for an entirely different epoch of climate stability. Compounding this regional vulnerability is the presence of Super Typhoon Bavi, which continues to operate as an active, high-intensity thermodynamic engine in the Western Pacific. The coexistence of two distinct cyclonic systems complicates the macroscopic fluid dynamics of the entire basin. While the remnants of Maysak dismantle the inland water control networks, Bavi acts as a massive offshore energy sink, altering the broader pressure fields and potentially reinforcing the very atmospheric blocks that caused Maysak to stall in the first place. This dual-front meteorological reality leaves regional forecasters in a state of absolute mobilization. The stability of the entire East Asian infrastructure network is effectively being tested by two separate failure modes simultaneously, one driven by the extreme kinetic violence of wind speed and maritime storm surges, and the other driven by the silent, high-duration saturation of an immovable rain machine. The interaction between these two systems means that the stress on the regional emergency response network is not merely additive, it is multiplying. Ultimately, the resolution of this event will not be dictated by administrative declarations or geopolitical boundaries, but by the raw physics of material limits. The true indicators to watch moving forward are strictly quantitative. Analysts are tracking the specific cubic meter per second discharge rates of northern spillways, the precise tracking coordinates of Bavi's path, and the statistical escalation of the casualty and displacement metrics as rescue teams penetrate the isolated interior villages of Guangxi. The initial numbers, 300,000 affected, 50,000 evacuated, will serve as the baseline historical marker for an event that redefined the danger parameters of weak tropical systems. The enduring lesson embedded in this catastrophe remains unchanged. A storm does not need to possess record-breaking wind speeds to achieve catastrophic erasure. It only needs to lose its steering current, stop moving, and continuously convert maritime moisture into a localized vertical wall of water. Whether the infrastructure of the surrounding provinces survives the coming days is a question that will be answered by the concrete, the soil, and the unyielding logic of structural engineering under maximum load. The final assessment of this hydrological crisis requires a rigorous synthesis of the mechanical realities that govern both our atmosphere and our built environment. When we analyze the complete life cycle of Typhoon Maysak, the data forces a total recalibration of how civil engineering defines environmental threat levels. For generations, public risk perception and emergency protocols have been tethered almost exclusively to wind velocity metrics, cataloging storms by the destructive power of their kinetic bursts. Yet the systemic collapse across the Guangxi Zhuang Autonomous Region proves that a low-velocity, high-duration system possesses a far greater capacity for absolute regional erasure. The physics of a stalled system dictate that the total volume of precipitable mass delivered to a localized coordinate operates independently of maximum sustained winds. When an atmospheric blockage halts a storm, it transforms a moving hazard into a stationary hydraulic forge. This forge continuously pulls moisture from maritime sources and converts it into a vertical column of water that systematically exploits every microscopic vulnerability in the regional infrastructure. This brings the analytical focus squarely onto the material limits of the water control networks themselves. The aging reservoirs, earth embankments, and concrete spillways across south-central China were designed around historical probability distributions that no longer accurately reflect the thermodynamic boundaries of the modern biosphere. An infrastructure grid designed to survive a calculated return period of 50 or 100 years becomes fundamentally obsolete when confronted with a single-day precipitation event exceeding 700 millimeters. When the input volume eclipses the design storm threshold, the entire network enters a phase of nonlinear failure. The Luonan Reservoir breach, the overtopping of the Yunbio, Sancha, Chaiwan, and Laiwang facilities, and the subsequent isolating of over 300,000 citizens are not isolated instances of structural negligence. They are the deterministic consequences of a macro system being forced to operate outside its engineered equilibrium. When multiple safety barriers fail concurrently within the same saturated watershed, they create an additive hydraulic load that downstream structures simply do not possess the structural capacity to buffer, completely fracturing the logistical response of human emergency frameworks. Concurrently, the scientific deconstruction of alternative narratives regarding artificial modification highlights a profound human cognitive bias. Faced with the terrifying realization that minor, unsteered natural systems can completely dismantle major industrial infrastructure, public discourse frequently invents hyper-complex myths of targeted weather weapons or clandestine demolition. This impulse seeks to replace a terrifying systemic reality with an identifiable human adversary. Yet, as the basic thermodynamic math demonstrates, the energy budget required to stall a tropical cyclone over a singular Chinese county involves a power output that matches a significant fraction of the entire energy generation of the human species. The physical fingerprint of this disaster is entirely natural. It is the raw, unyielding signature of water winning against earth and concrete. It is the consequence of an atmosphere that holds approximately 7% more moisture for every degree Celsius of global thermal elevation. This extra water vapor expands the total capacity for extreme precipitation events, moving what were once highly improbable tail distribution anomalies into the baseline operational reality of modern civil infrastructure. As the physical threat parameters move toward Hunan, Hubei, and Jiangsu, and with Super Typhoon Bavi still modulating the Western Pacific Basin, the ultimate lesson of this event remains fixed. The vulnerability of our collective socio-economic architecture does not scale with the dramatic violence of the wind. It scales with the duration of the stress and the structural deficits of our protective barriers. The cascading failures in Guangxi serve as an early, highly detailed blueprint of a global civil engineering crisis. The concrete has reached its ultimate shear strength, the soil has hit absolute saturation, and the rivers have demonstrated the true limits of human containment. The unfolding reality across these interconnected provinces will now decide whether the lessons of the Banqiao disaster have been fully integrated into modern emergency networks, or whether human engineering remains dangerously unprepared for a planet where the sky can simply stop moving and refuse to stop raining. The ultimate resolution of this cascading system failure brings us face to face with the hard physical boundaries of built infrastructure when it is forced to contend with an altered atmospheric regime. As the remnants of Typhoon Maysak continue to saturate the landscapes of south-central China and threaten the highly populated networks of Hunan, Hubei, and Jiangsu, we are witnessing the raw operational boundaries of modern civilization. The metrics from Binyang County, where 713 millimeters of water fell in a single day, demonstrate that our protective barriers are only as resilient as the historical assumptions used to design them. When a weak, low-velocity storm stalls and drops an annualized volume of water onto a single coordinates within 24 hours, it completely invalidates the statistical models that engineers call return periods. The concurrent structural collapse and overtopping of the Luonan, Yunbio, Sancha, Chaiwan, and Laiwang reservoirs were not isolated instances of mechanical error. They represent the deterministic threshold where structural safety margins are completely consumed by a massive, concentrated hydraulic load, leaving over 300,000 people trapped in the structural gap. This failure mode highlights a critical flaw in how human systems evaluate threat vectors. We have historically allocated our risk mitigation assets toward high-velocity, high-visibility anomalies, measuring the danger of tropical cyclones by the physical violence of their sustained winds. Yet the systemic breakdown across the Guangxi Zhuang Autonomous Region proves that duration is the far more lethal variable. A weaker storm that refuses to leave will systematically outkill a fast-moving monster because it concentrates its entire moisture cargo over a fixed geographic coordinate. When the macro-scale steering currents of the atmosphere fail, the natural and engineered systems below are forced to process a continuous, vertical stacking of mass. This overloading swiftly triggers a non-linear cascade, where the failure of an upstream node automatically injects uncalculated kinetic energy and fluid volume into every downstream barrier, fracturing the logistical response capacity of human emergency frameworks and forcing rescue teams to divide their thinned resources across multiple concurrent emergencies. Furthermore, the scientific deconstruction of speculative alternative narratives regarding weather modification or intentional sabotage underscores the absolute scale of this natural forge. The suggestion that human installations or targeted technologies could deliberately steer or anchor a tropical system collapses when evaluated against basic thermodynamic data. The power flowing through a mature typhoon operates on an order of 74 trillion to 1 quadrillion watts, an energy budget that dwarfs the total industrial output of human civilization. The forensic signature left across the watershed, the overtopping of crests, the rapid hydraulic erosion of earth embankments, and the expansive 50-meter fissures is the unmistakable fingerprint of infrastructure simply being overwhelmed by volume. It is the manifestation of a warmer biosphere, where a 7% increase in atmospheric water vapor per degree Celsius of warming shifts the probability curves of tail distribution storms into the everyday operational reality of aging engineering grids. We are left with a sobering, highly definitive conclusion regarding the structural boundaries of our environment. The events in Guangxi are not a temporary departure from normalcy, but a precise demonstration of structural limits under a maximum load. When the sky stops moving and refuses to stop raining, the safety of millions depends entirely on whether our collective water control networks can withstand an epoch where the rules of historical weather patterns no longer apply. The initial baseline numbers of this catastrophe catastrophe. The thousands displaced, the rising casualty curves, and the declaration of a level 1 flood emergency in Nanning serve as a stark warning label for the future. The concrete has met its ultimate shear strength, the soils have hit absolute saturation, and the rivers have revealed the definitive boundaries of human containment, leaving us with the uncomfortable reality that our built world is operating on borrowed time against the physics that never negotiates.